Hello everyone, I'm OJ from Chongqing University of Post and Telecommunications. I'm honored to be able to participate 60th EAI International Conference on Communications and Networking in China. The topic of my speech is robust sound event detection by a two-stage network in the presence of background noise. The next speech is divided into 6 parts: Introduction, Neural Network Framework, Loss Function, Data, Results, Conclusion. First, Introduction. The purpose of Sound Event Detection (SED) is to detect specific sound events in different sounds and to locate the onset and offset times of target sound events present in an audio recording. In the case 2017 challenge, the same of task 2 is detection of real sound events. Real means that target sound event, baby cry, glass break, gunshot, will occur at most once with a 13-second recording. According to the above figure, the blue box is the target sound event, and the target event is covered by the loss of heavy. In real sound event detection, the loss of surrounding harsh environment may cover the target sound event and cause the performance of the ECD system to decrease. The more conventional idea is to denoise the noise speech before sound event detection. However, this is a complicated matter. Evaluating the methods used in the past, especially in the field of speech recognition, there are basically two models to deal with the two stages of speech enhancement and detection. This scheme can improve the performance of ECD system, but at the same time, there are some shortcomings in two aspects. First, two different models are used to handle two different tasks separately, especially during the inference period. It is also necessary to run the two models separately in sequence, which is relatively redundant and complicated. Second, during training, the audio distortion caused by the denoising system will cause the performance of the ECD system to serious degrade. Okay. Is there a model that handles both speech enhancement and detection tasks at the same time? We proposed a two-stage deep learning network for ECD. Next, neural network framework. Figure 1 shows a schematic diagram of the proposed system, which consists of a denoise block and a ECD block. The structure of the denoising block and the ECD block are built by the unit architecture and the multiple CNN architecture, respectively. In the proposed network, we first train the noisy network and the ECD network separately so that the network learns the weights of the corresponding tasks. After that, we join in train the two models to make the network learn the ability to handle two tasks at the same time, which is relatively difficult to combining essentially two different tasks. Finally, an optimized system that can perform the noisy and the ECD task at the same time is obtained. In addition, we propose a new weighted loss function, which can punish the distortion caused by the noisy network to associate the front and back models. This loss function plays an important role in improvement of model performance. Next, loss functions taking into account that the front-end enhancement block will produce a certain distortion of the speech, thereby affecting the information of the target sound event in the audio. Therefore, we use a multi-text weighted sum method to punish the distortion caused by the first stage, the noising block, so that the network learns in the right direction. Where f function represents this noising block, the symbol is Euclidean norm, L norm. Lambda denotes the penalty factor of the denoising block. L theta presents cross-entropy loss function. P and Q are the output probability and label of the proposed model's responsibility, respectively. When the denoising block produces large distortion, loss function will punish the denoising block and force the network to learn in the correct direction so that the effect of distortion is minimized. Next, data. The dataset is comprised of development datasets and evaluation datasets. The development dataset also consists of two parts, tree subset and text subset. Participants are allowed to use any combination of the provided data for training and evaluate their model on the text subset of the development dataset. Ranking of submitted systems is based on their performance on evaluation dataset. We use the provided sensor size to generate 5,000 mixture for each category for network training. The event to background routes are -6, 0, 6 decibels, and the event present probability is set to 0.9. Default value 0.5 in order to gain more positive symbol and mitigate the problem of data imbalance. We use the development test subset to optimize our model and finally evaluate is on the evaluation dataset. Next, results. The error and F-score of the proposed model and other models are shown in Table 1. Results show that the proposed outperforms the baseline due to the noise suppression. Compared with other noise robustness models, the performance of the proposed two-stage is also superior on evaluation dataset, which indicates that the proposed network is more robust to noise. In addition, using WMT as the loss function can further improve the performance of the proposed ACD system, which ratifies that the WMT method above can reduce the distortion caused by the denoising block. Table 2 shows performance comparison of the proposed model and other state-of-the-art ACD models in terms of error and figures F-score. Compared with other proposed approach, the performance of our model is also competitive. It is worth noting that the final model we get is a single model that performs denoising and sound event detection at the same time. Next, to better understand our proposed network, we versionized the output the denoising block in the two-level network. Figure 2 shows that the two-stage model we proposed have actually learned how to suppress noise. We select an audio with a baby cry to visualize, and the baby's crying occurs from 20.59 seconds to 21.53 seconds, which is marked by a blue free. The target event is under park noise. After noise suppression, the target sound becomes clear. This confirms that our proposed network achieves the dual task of denoising and detection at the same time. Next, conclusion. In order to solve the impact of noise on ACD, in this work we propose a two-stage model to perform the joint task of single denoising and ACD. In addition, we propose a loss function that is conducive to network optimization. Our system can achieve the best performance on decays in evaluation datasets. Compared with our noise robust networks, the joint network performance is better. The large improvement demonstrates the benefit of introducing the denoise block. Thank you.